As a propulsion systems architect, I've really spent the better part of 2 decades obsessed with one single goal, making urban air mobility a reality. So today, we're not just going to talk about vague concepts. We are going to break down the actual engineering specification for the very heart of the P-13 hybrid aircraft, its energy storage system. This, right here, is the blueprint we're using to build the future of flight. We all have this dream of flying over the city, skipping all that traffic. It's a powerful idea, right? But it all boils down to one massive problem. The single greatest barrier, the one thing holding it all back, is creating a power source that can handle the incredible and frankly contradictory demands of vertical flight. And this visualizes that core challenge perfectly. We call it the impossible triangle. Think about it. You need extreme, unbelievable power to lift straight up. You need high energy for decent range. And of course, you need absolute, uncompromising safety because, well, you're in the air. The problem is, these three things are always fighting each other. If you optimize for one, you almost always take a hit on another. Our entire job as architects is to engineer a way to master this conflict. So how do we do it? Well, the key to solving this triangle isn't just to build a bigger, better battery. It's to completely redefine the battery's role. Our entire design philosophy is built around a concept we call the power buffer. Okay, so in a P-13 hybrid system like ours, the energy storage system, or ESS, is not the main source of energy for the whole flight. That's what the thermal engine is for. Instead, the battery becomes this incredibly smart, dynamic system with two very specific jobs: to act as a power buffer for when we need a massive burst of energy and to serve as the ultimate safety lifeline if anything ever goes wrong. And what's so cool about this diagram is how it really shows you that philosophy in action. The thermal unit is the workhorse, providing that steady, efficient energy for cruise flight. But the ESS, it steps in with a huge surge of power for takeoff and landing. And at the same time, it's always on standby, ready to take over in an instant and give you the power you need to land safely if the main engine ever fails. It's both a booster and a bodyguard. So how do we actually put this philosophy into practice? Well, we attack the impossible triangle by breaking it down into three core design pillars that cover everything: extreme performance, absolute safety, and thermal containment. First up, extreme power. In a normal electric car, the battery is designed for energy. It's a marathon runner. But in our hybrid system, the ESS is an Olympic sprinter. Its number one job is to deliver an absolutely immense surge of power to get the aircraft off the ground. We're talking a demand that can be 7 to 10 times higher than what's needed for cruise. And we quantify this with targets that are completely non-negotiable. Now, sure, energy density and cycle life are vital for making this a viable business. But just look at that pulse discharge rate. We need to deliver over 10 C. That basically means unleashing the battery's entire power potential in just a few minutes, all focused into a 30-second burst. That is the raw brute force you need to beat gravity and lift this thing straight up. You just can't get this kind of performance with off-the-shelf car batteries. It's impossible. We have to go right down to the molecular level with aviation-grade chemistry. High nickel cathodes for energy, a silicon carbide anode to cram in more lithium ions, and a semi-solid electrolyte that makes it way, way harder for a thermal runaway to even start. This is a cell designed from day one, from the ground up, for flight. Okay, pillar 2, absolute safety. Our design target isn't just very safe. It's a specific number mandated by aviation authorities like EASA. And that number is a probability of catastrophic failure of less than 1 in a billion flight hours. That's the bar. That is the standard we have to meet, period. So how in the world do you achieve a number like that? The first principle is simple. You design for failure. You assume things will go wrong. On the left, you see a single point of failure. One little fault, and the whole system goes down. Bad news. On the right, that's our multi-lane fail operational architecture. We use multiple, totally independent battery packs and power lines. If one lane fails for any reason, the others just keep on working, completely unaffected, ensuring the aircraft can always fly to a safe landing. And that leads us to our third and maybe most critical pillar, thermal containment. Because even with a 1 in a billion target, we have to assume the worst-case scenario will happen someday. An internal failure in a single tiny cell, and we must be able to control it completely. We engineer for this event by first understanding its physics. You see, a thermal runaway isn't a simple fire. It's a violent, super fast chain reaction. This chart shows you that incredible acceleration. It starts around 184 degrees Celsius and then just skyrockets in a matter of seconds. We map this exact profile to build our defense.
And that brings us to the peak temperature, over 800 degrees Celsius. Just to put that in perspective for you, that's hotter than the lava flowing from many volcanoes. The system has to be designed to withstand and contain that extreme heat, all inside one tiny failing cell.
So our solution is a multi-layered containment system. It's a 1-2 punch. First, passive protection. We use advanced insulators like aerogel between every single cell to stop the heat from spreading to its neighbors. Second, active management. We design these dedicated channels that safely vent all that superheated gas and smoke outside the aircraft, far away from any people or critical systems. The failure is completely contained and controlled. But, a design is just a theory on paper. How do we prove with 100% certainty that it actually works? Well, we subject it to a grueling validation process that starts in the digital world and ends with, physical destruction. This is our validation journey, and it's a very methodical progression. We start with software simulations. Then we test the physical hardware by injecting all sorts of faults. After that, we integrate the entire system, batteries, motors, cooling, everything, on a full-scale ground test rig we call the Iron Bird. And only then, after all that, do we move to the final step, intentionally triggering failures to prove our safety systems work in the real world. And that destructive testing is just one part of a whole gauntlet of certification trials. We trigger thermal runways on purpose. We short-circuit the system. We subject it to the pressures of high altitude. And yeah, we even drop the entire battery pack from 50 feet onto solid concrete to prove its structural integrity in a crash. It absolutely must survive. So these 3 pillars of design, power, safety, and containment, validated by this brutal trial by fire, they all come together to form the verified blueprint for a new class of certified, safe, and truly reliable aircraft. And this is the result. It's a system built not on one single idea, but on 5 mutually reinforcing pillars. You've got extreme power for performance, fail operational safety built into the architecture, absolute thermal containment, mission readiness through smart management and fast charging, and finally, structural integrity that's been proven through a whole lot of tough testing. Together, these are what finally solve the impossible triangle. The key takeaway here, the thing to really remember, is that this isn't just about building a better battery. It's about establishing the foundational certifiable technology that the entire future of urban air transportation is going to depend on. This blueprint is what makes commercial success even possible. And this technology is not standing still, not for a second. What we've just walked through is the blueprint for today. But right around the corner, we're looking at solid-state batteries that will shatter energy density records. And beyond that, the really exciting part, AI-enhanced battery management systems that won't just react to failures, but will actually predict them weeks in advance. Ultimately, all of this brings us to one final critical question. This incredible level of uncompromising aviation-grade engineering is what will make these aircraft fly, but it's also what will earn the public's trust. The dream of urban air mobility doesn't just rest on technology. It has to rest on a foundation of proven, absolute safety.